In late 2015, enterprise Java environments, including WebLogic, WebSphere, and Jenkins, experienced a massive wave of remote code execution attacks. Attackers exploited zero-day vulnerabilities to take full control of systems through a single, untrusted data stream. The vector for these breaches traced back to the widely used Apache Commons Collections library, specifically a class named Invoker Transformer. Yet, the Invoker Transformer contained no malicious code. The developers had not made a logic error, nor was the codebase hijacked. The class was operating exactly as specified, transforming objects within a collection by invoking a method using reflection. The vulnerability stemmed directly from the underlying architecture of Java itself, specifically how the Java virtual machine natively reconstructs serialized data. Because the flaw exists in the core architecture of object reconstruction, standard network firewalls and source code patches cannot provide a structural defense. In response to CVE 2015-4852, the security industry reacted with standard perimeter defense tactics. Teams deployed web application firewalls and attempted to blacklist the Invoker Transformer class outright. The Apache community issued a fix that disabled the serializability of Invoker Transformer by default. This modification immediately broke backward compatibility, crippling any application that legally relied on serializing the class for legitimate operations. Despite breaking production systems, the patch failed to stop the attacks. Security researchers quickly mapped out over 20 alternative payload paths that achieved the exact same result without requiring the Invoker Transformer. This exposes the whack-a-mole fallacy of mitigation. Security teams blacklist one specific class, and attackers simply weaponize another from the thousands of available libraries on the class path. Blacklisting classes treats the symptom of the attack. It leaves the underlying execution mechanism entirely intact and exposed. Serialization converts a memory object into a sequence of bytes for storage or transmission. Deserialization is the reverse, rebuilding that object in memory. This animated diagram illustrates a critical timing gap in Java's instantiation process. On the left, we see the developer's expectation. The system reads the bytes, verifies the object type, and only then executes code. On the right, we see the actual JVM behavior. The system reads the bytes, executes custom read object logic, and then checks the final object type. Attackers target this exact gap. They send a malicious byte stream to an application that eager JVM logic begins to reconstruct immediately. The platform code automatically invokes the read object methods of the classes specified in the stream, entirely outside the developer's control. This pre-existing logic executes before the final object is fully formed, meaning the application has no opportunity to reject it for being the incorrect type. By the time Java's strict type system evaluates the object to determine if it is safe, the payload has already achieved execution within the JVM. A gadget is a pre-existing benign method that currently sits legally on the application's class path. Tools like Isoserial construct payloads by chaining these gadgets together. They route the output of one benign method into the input of another until the application is forced to invoke dangerous functions, like runtime.execute. By chaining the read object method of annotation invocation handler to the reflection capabilities of Invoker Transformer, an attacker achieves arbitrary command execution. The ultimate failure of the blacklist approach is the existence of the golden gadget chain. Golden chains contain zero third-party dependencies. They are constructed entirely from native Java runtime environment gadgets. Blocking a golden chain requires disabling native elements of the JRE itself, an action that will crash the JVM and the application running on it. You cannot remove the native building blocks of the language. Therefore, deserialization cannot be solved by simply altering the codebase. The mechanical reality of gadget chains explains why standard DevSecOps pipelines fail to catch deserialization exploits in production. Web application firewalls lack deep application context. They cannot reliably inspect complex serialized binaries moving through HTTP or RMI protocols without generating false positives. Static application security testing identifies early code patterns but lacks runtime context. It cannot map highly dynamic logic or evaluate deep transitive dependencies during execution. Dynamic and interactive testing validate exploitable behavior in staging environments, but their visibility is strictly bound by the execution paths triggered during quality assurance testing. Attackers can structure deferred execution attacks, such as hiding payloads within the finalize method. This allows the gadget chain to execute long after standard deserialization checks are complete, bypassing testing phases entirely. Relying exclusively on pre-production testing and perimeter firewalls leaves a permanent, exploitable execution blind spot in the live environment. To close this blind spot, the application must be defended at the exact layer where the vulnerability materializes, the execution layer. Runtime Application Self-Protection, RASP, actively instruments the JVM in the production environment. During a deserialization operation, RASP creates a dynamic, restricted compartment around the specific thread processing the byte stream. Legitimate objects reconstruct cleanly, but malicious gadget chains attempting to execute system commands are blocked. This architecture allows necessary third-party libraries, like Apache Commons, to function normally for legitimate tasks, while neutralizing their ability to be weaponized for remote code execution. This level of protection is deployed using declarative security as code, allowing teams to manage runtime behavior via explicit policy rather than source code rewrites. A mature 2026 AppSec posture integrates SAST in the IDE for early pattern detection, DAST and IAST for staging validation, and RASP as a context-aware defense operating directly in production. True application security requires abandoning the illusion of a hardened perimeter. Applications must defend themselves from within at the exact moment of execution.